Hello friends, welcome back to the bench. Now today's gonna be a short video because it's my son's birthday. He's turning 9. He's becoming a big boy now. So before I get to the celebratory part of my day, let's take a little recap of what I did last night as far as the temperature control circuitry or temperature controller, and what considerations you might take into account when designing such a device. So what we have is an ESP32 microcontroller, or actually, yeah, it's a microcontroller, but this is dual core with Wi-Fi, Bluetooth, very powerful device. The code that I wrote for this is not really utilizing that, and it can be just as well uploaded to Arduino Nano. It will obviously, you would have to repin it, adjust the pins, because there's only one ADC input on the Nano, and actually here we need two ADC inputs. I'm not sure, maybe there's more than one on Nano. In either case, this is overkill, at least for now, but this is very good device to run your tests on, because at any point you can just expand it as much as you like, be it, you know, connect to it with Bluetooth or connect it to Wi-Fi, and, you know, control your heater or preheater with Wi-Fi or with your phone. So it gives you a lot of abilities if you wanna play around with it. In this case, we're not utilizing any of that. What we have is a thermistor. Now this is very nice sensor that you can buy for Arduino, and it has two outputs, digital output and analog output. Analog output gives you the actual voltage depending on the temperature. Digital output just goes high or low depending on the position of this potentiometer here. Now for the actual control, I utilized our previous circuit. So I just connected power to it, and our digital output from the ESP goes directly, controls the thyristor or whatever it is. But it actually controls the transistor over here. We have temperature control, the hold button, which is not implemented yet, but this is something that I would like to have on my heater. The idea is very simple. Once the preheater reaches the set temperature, it turns off and it just tries to stabilize that temperature. But as soon as you start heating from the top, the preheater will never turn on, because we're measuring the temperature of the board. So we basically lose heating from the bottom. So what this button will do, if I press it, it's just gonna keep pumping some energy into the heater regardless of what temperature we have. And this is just for the purpose of those 2, maybe 5 minutes when we are heating the board from the top, just before we remove the component that we want to remove. We have OLED display. This is I2C, very simple display. Much better solution than the segment displays, because it requires just 2 pins for clock and data, and obviously on I2C you can place more than one slave device. ESP32 is not limited. Any output or any input can be used as an I2C. So that's another advantage of using ESP32 versus Arduino Nano or Arduino Uno, what have you. We have a little buzzer and a diode that indicates whether the heater is on or off. And we have a heater over here on which we will place the thermistor. We supply it with 120 volts AC mains. And for that purpose, I had to remove the microcontroller so it doesn't interfere with our controller. And that's pretty much it. Everything is supplied by 5 volts, and let's give it a test. So when I turn it on, unfortunately it will be flickering on the screen. There's nothing I can do with that. This has nothing to do with the stable if supply voltage. This is actually just the refresh rate of the screen. As you can see, we're using percentages, so I can go to 100% or turn down to 0%. Or at least, as you can see, it's not calibrated well enough. It doesn't go all the way to 0, and it's not too stable, as you can see. Not super stable, but it's a lot more stable now that I added a big capacitor on our supply rail, another capacitor here, the capacitor on the digital input or the analog input that comes from the potentiometer. That stabilizes it quite a bit, but as you can see, it's not stable. That's not really an issue at the moment. This is not our consideration at the moment. Our main considerations, though, are, first of all, when you're designing circuit like that, when you want to control the temperature, the first consideration is how much energy are you going to push into the heater, and what will be the curve of how temperature rises. Because right now, and you would think that this is very simple, and in a way it is, you just turn on the heater. As you can see right now, the heater is on. The LED also indicates that. So now we're waiting until we reach the set temperature. Temperatures are in percentages because of this potentiometer. So we don't. It's kind of hard to calculate with this device. It would be much easier if I just had a thermistor and a resistor. That is much easier to calculate. But on top of that, you do need a piece of information from the data sheet of the thermistor. Now this thermistor doesn't come with a data sheet, so we don't have that number. So it can be, we can just guess it and just, you know, test it in reality, and we can get it pretty much close enough to get relatively precise temperature. It doesn't have to be too precise, obviously. But that's why we're just using percentages, just to go around that problem. It's not really necessary. It's not that relevant at the moment what 10% the temperature is. And the resistance curve, the resistance changes curve of the thermistor is not linear, so we need to use logarithm to actually calculate the actual temperature. That's why the 50% doesn't mean that it's within a half of the temperature range. Our temperature range is roughly 0% is roughly maybe around 35 degrees, while 100% is roughly around 150-160 degrees, which is a limitation of this thermistor. Now let's get a thermal imager so we can see the actual temperature, and that's roughly how we would calibrate it. Now the second consideration is what we call hysteresis. I'm not sure what exactly it is called in English, but the idea is that if our temperature goes, right now it's set to 11%, our temperature goes to 11%, then you're in this region where the heater is going to be turning on and off for it's just going to kind of be unstable, basically. The easiest way to go around that is to use the two different thresholds at which you turn on and turn off. So if we're set to 11%, then the heater turns off at 12% and turns on at 9% or something like that. Now, if we're only controlling on and off switch, so say this is a relay switch, which is not in our case. But if it's a relay switch, then obviously this is how it's supposed to work. There's nothing you can do with that. But since we're using a thyristor, we can actually utilize something close to PWM signal. Actually the exact PWM signal pretty much. Which means instead of just relying on be it 1 or 2 thresholds to turn on and off, instead we're considering how much difference between set and current temperature is, and based on that we pump more energy. As the temperature gets close to our threshold, we reduce power and we just slowly bring the temperature up. That is a lot more efficient. That gives you a lot better accuracy when it comes to setting temperature. And we should be able to see this right now when the heater turns on, goes to 11%, then it turns off. The temperature will still rise because the heater will not heat up immediately. After you cut off power to it, the temperature will still be going up. So maybe we'll go to even 50% or 60%. So that is the consideration number 2, which is relatively important if you want to keep the temperature stable. Okay, now we're gonna turn on the power. Heater is on, and we should start observing the heater heating up. And we see that we went to 100 degrees pretty quickly. Now we reached roughly 10% as we were supposed to, and note that we went already to 30%, and now it's slightly going down. 98 degrees on the heater. So first reason for that is that we have very poor connection between the thermistor and the heater in this case. The majority of the heat transfer is the air. The thermistor is just close to the heater. It's not within the heater. But that's pretty much what we're gonna have to work with, because we want to put this thermistor or the thermocouple on the board and measure the temperature of the board. Which means we're never gonna have a good connection. We're never gonna know exactly what the temperature of the board is. So to account for that, we need to modify our programming. So point number 1 is to measure the distance between set temperature and current temperature, and based on that start applying energy accordingly. Now the temperature is dropping. We are down to 67 degrees on the heater. Our temperature in percentage shows around 20, which was set to 9. And again, as soon as the temperature goes down to actually 9, it will again jump to 30. So this is the whole issue with this design. Now you're probably wondering why I'm working on this. I did order an actual professional, well, Chinese professional temperature controller with thermocouple. The ranges to which ranges to 400 degrees, which is more than we need as long as we're measuring the temperature of the board. But we'll see how well can that device stabilize the temperature, because what we need is a stable temperature, which means we have to be very conservative with how much energy are we pushing to the heater. and the heater turned on because we dropped to 9 and turned off immediately. Right? But now we're gonna see the fallout of that tiny energy being pushed into the heater. And again, we're at 20, 21. Actually, the second time around, it didn't spike all the way to 30 because initial cycle needs to heat up the heater from the base temperature, from the room temperature, all the way to the set temperature. And there's going to be a delay, obviously. So when we start the heater, we shouldn't be pushing all the energy. So we should work in cycles. This should be turn on for a second, turn off, read the temperature. Turn on for a second, turn off, read the temperature again. And based on that, we can adjust. Now the temperature is not rising quick enough. Let's turn it on for 2 seconds, then turn off, read the temperature. Then wait 2 seconds, or maybe wait only 1 second. So basically it needs to be a lot more intelligent than we have it right now. But this is just to show you the consideration that you need to take into account when working on a device like this. Now the heater turned on again and turned off very quickly. Now this seems relatively stable. It's actually a lot more stable than I expected it to be. Mainly because our entire circuit is on the breadboard, so that and now you see we fell into this unstable position, unstable threshold, where the heater just goes crazy because our measurements can be off by 1%, 2%. We have a little fan, the ceiling fan, blowing on top of us on the minimum speed, but still it's going to be blowing on the thermistor. So what temperature are we stabilizing at 9%? It looks like around 60, 70 degrees. It is indeed stabilizing roughly within that region. So technically it works. As you can see, it doesn't take too much to design a circuit like that. It can also be designed a lot easier with just discrete components, using an operational amplifier as a comparator. However, we want to utilize microcontroller so we can have a nice display and some functions like the hold to give it some extra features. Okay, so this is where we at with the circuitry right now. As you can see, the temperature is fluctuating. The heater turns on and off because we're within the region where it becomes unstable. So that's the problem number one. Problem number two, heating. We're heating way too aggressively. And I'm afraid that is going to be the problem of that pre-built temperature controller that I ordered from China. We'll see how well that will perform. But this is something that I expect is going to be the problem with that one. We'll see what actual temperatures are. How well can we stabilize temperature on the heater, and actually not on the heater, on the board. We'll see how aggressively it pushes the energy, and if I predict correctly, it will just work just like this, basically just turning on and turning off without consideration how quickly it should heat it up. So we'll see if we can actually use the pre-built Chinese controller, or do we have to actually build the circuit ourselves. Now, if you're interested in a schematic for this or the code, hit me up on Discord, but I assure you there's nothing fancy as far as the coding goes, at least for now. Right now it is written just like for Arduino Nano, So it's a simple delay, simple loop. There's no timers, no multi-cores, no multi-threading utilized. However, to achieve the good effects, controlling how much energy we're going to push into the heater, we need to utilize multi-threading. We're going to have one thread that will be receiving control information and turning on and off the heater, depending on how far off we are from the set temperature. So once I actually confirm that I have to build it because the off-the-shelf components will not do it, I will design it the way it should be designed, but that's going to take me a little while. Multi-threading is not easy. Debugging these microcontrollers is also not easy, especially when you don't have the interface to actually be able to debug code as it runs on the device. The other problem is that with the heaters and all this, there's a lot of interference. So if you have a serial connection from your computer to the microcontroller, often it is interrupted. There's voltage spikes, what have you. I'm not sure, electromagnetic interference perhaps. There's a lot of power that needs to be pushed, or considerably a lot of power compared to 0.3 watts that this consumes. So that interferes, that makes the process very lengthy, as opposed to working on the PHP script or just some C++ based application for the desktop. Now, I hope you found this useful. Thank you guys very much for watching. I do appreciate you, and I shall see you in the next one.